Hello students, we are done with section 1 and let's go to section 2. Section 2 is mainly about this theorem, the rank theorem. It applies to all linear maps defined in a finite dimensional vector spaces. Let V and W be vector spaces and let F from V to W be a linear map. Then, dimension of the image plus the dimension of kernel add up to the dimension of the original vector space V. Here, the original vector space must be finite dimensional. If this is infinity, then of course this identity is meaningless. Now, is that enough? If this is finite dimensional, then are these two also well defined? The answer is yes. Why? How about the kernel? Kernel is actually a subspace of V. Therefore, if V is finite dimensional, the kernel has dimension less than or equal to the dimension of V because this is subspace, so certainly it is finite dimensional as well. So that part is okay. How about the other part over here? How about the image? Is that also well defined? The answer is yes again, from theorem 1.4, or if you want to look at theorem 1.5, either way, the dimension of the image is less than or equal to the dimension of V. So yes, this too is finite dimensional. And this identity has, well, we have yet to prove it, but at least it is well posed. One more thing before going over to the proof. Here in this identity, we use V and we have image of F and kernel of F. And a conspicuous absence is W. This one has nothing to do with W, and the reason is that's unnecessary. As a matter of fact, the target is unnecessarily large. If you have a map from V to W, that means map from V to image of F, and the image of F is part of W, but the members of W, which have nothing to do with the image, doesn't have anything to do with F either, so they're just out of consideration. And this is perfectly fine because the image of F is by itself a vector space, and it is involved here, as you can see. Here's an example to see that better. A map from R3 to R2. Okay, that's a linear map, you can check that. And then you can artificially create a map from R3 to R infinity by putting a bunch of zeros here. But then again, this is cheating, it's meaningless. What's the difference between the second map and the first map? Nothing, absolutely nothing, because these zeros are nothing. So in short, it's not surprising we don't have any W involved in there, because from the beginning, it is meaningless. You have to stop at the image, and that image is indeed involved here. By the way, this paragraph summarizes what we talked about earlier about the use of theorems 1.4 and 1.5. Okay, so much for the remark, and let's go to the proof. Are you ready? Okay, let's begin, and let's begin with some warming up, some trivial cases first. First trivial case, when V is just a zero-dimensional vector space, it has just zero vector and nothing else. This is the smallest possible vector space. You cannot have an empty set. The definition of vector space that we talked about in, was it week 3, week 4, and was it week 2, week 5? I don't know, excuse me. The definition of vector space started with non-empty set, so it cannot have an empty set. It needed at least the additive identity. And yeah, 0 is the additive identity. So this is the smallest possible vector space. In that case, everything is zero-dimensional. We have 0 equals to 0 equals... We have 0 plus 0 equals to 0. Trivial case. Why did I spend so much time on this trivial case? Sorry about that. Next case, the image is just trivial space, so the dimension of image is 0. In that case, image is just 0 vectors, so all the vectors are going to 0 vector. F is the 0 map, so entire V is the kernel. You see, image consists of only 0 vector. That means all the image vectors are 0, which means F is just 0 map. Everything goes to 0 vector. In other words, V itself is kernel. Every vector in V belongs to kernel. So we have to have 0 plus n equals n because V and kernel are the same. These two are the same, and this one is 0. Third case, when kernel is 0, so this is 0-dimensional. In that case, we use theorem 1.7. V1 through Vn is linearly independent, then f of V1 through f of Vn is linearly independent too, under the assumption that kernel is 0. Consequently, f is a one-to-one map. If these generate, then these generate as well. That's part of 1.4. So combine those two, and what we get? V1 through Vn is basis, then f of 1 through f of Vn is basis. In short, they all have the same dimension. One is n dimension, the other is also n dimension. So what do we have? We have n plus 0 is equal to n. So in that case, we have the identity. So we took care of all the trivial cases. Now let's assume that both image and kernel have at least one non-trivial vector, and consequently their dimensions are strictly positive integers. Here is the main body. Let's assume that dimension of kernel is q and dimension of image is r, and they are positive integers. And what are the basis vectors of image? Let's go back to the definition of the image. And image is set of all image vectors. So arbitrary element of image of f looks like this, f of something. And then we need r vectors, so we name those as f of v1, f of v2, all the way over to f of vr. Let these be r distinct vectors that form the basis of image of f. And then kernel, let us select u1, u2, u3, all the way up to uq. I cannot select v1, v2 anymore because those are already selected, you see. These are taken. And then I don't want to select w1 and w2 and so on because it looks like they're coming from the target. So another character is necessary. I'm just using u1 through uq. I could have selected some other character, but I decided to select u1 through uq. And now, f of v1, f of v2, all the way up to f of vr, they belong to the image, which belong to the target w. And the inside, v1, v2, all the way up to vr, these belong to v. These belong to the original space, the domain. So what we are going to do now is take those v1 through vr from the domain, and u1 to the uq, which of course is from domain because kernel is part of V, and get those r plus q vectors from V, and we'll claim this is a basis of V. So we'll have to prove that. So this is what we claim. Now, if we have this claim, then we have to prove two things. If you have a certain set is a basis, then we have to prove, number one, it generates a vector space. Number two, it's linearly independent. Generate is first. We want to prove that these generate vector space phi. In other words, we claim any vector v is selected from capital V, then can this be written as a linear combination of v1 through vr? And then u1 through uq. That's what we have to prove. You see, this part green, that part blue, okay? That's what we have to prove. And then the next thing we have to do is linear independence. So if these add up to 0 vector, then all the coefficients and all the coefficients so we have to show this generators, and then later we have to show this linear independence. Okay, let's postpone this one. Let's consider this one first. This is what we want to prove first. For arbitrary vector from V, it can be written as a linear combination of these. Okay, let's begin. We select arbitrary vector V, and then apply capital F so that f of V belongs to the image. Then image of F has basis. That's the basis, and basis generate. Therefore, any image vector can be written as a linear combination of f of v1, f of v2, all the way up to f of vr. You see, bases have two properties, generating and linear independence. This part is about generating, so we are using the generating property. And then let's apply the properties of linear map so that this linear combination can be passed inside. So far, so good. Just property of linear map. And then here's a little bit ingenious step. Instead of writing as f of v is equal to f of that linear combination, I wrote it as 1 minus of the other is equal to 0. And then I highlighted this red part. Why did I highlight this part? Why did I subtract one from the other and then equal to 0 instead of leaving here? What's the advantage of this 0? That's because I wanted to get the kernel involved. We used the image earlier by taking the map F. I have to use the kernel. Image we already used. We took the map F. Kernel is related to 0 vector. So f of something is 0. That something belongs to kernel. So we want 0 vector involved in there. So that's 0 vector. And that's why I highlighted this part in different color. Okay, pay special attention to this equal to 0. And here's the next step. Equal to 0, all right. And then combine these two. F of v minus this linear combination. Nothing fancy. This is a linear map, so we can pass on all those linear combination inside. But we have equal to 0. And does it really help? Yes. F of something is equal to 0. Therefore, that something belongs to the kernel. Now, kernel has basis U1 through UQ. You see, this is basis. And then we are proving generation, so and kernels generate by U1 through UQ. So Y1 U1 all the way up to YQ UQ. We can generate this. The final step is easy. All I have to do is flip this to the other side, then we have the desired linear combination expression. So what did you get in the end? Arbitrary element V of the original vector space V is a linear combination of V1 through VR plus U1 through UQ, and consequently generated by these. Okay, one down, one more to go. Bases must be generators and that are also linearly independent. We proved the generation part. Okay, that part is done. And then we want to prove the linear independence. All right. Set the linear combination equal to 0, and we have to prove all the x's are 0 and all the y's are 0. All right. How do we do that? Of course, we have to set them equal to 0, set the linear combination equal to 0. And then we do something similar as before. Kernel and image. Image is about taking the map F. Kernel is it's going to 0 vector. We have to get those involved. Map first. Take the map F. So f of this big linear combination is equal to f of 0. Now, f of 0 is easy. F of 0 is always 0 vector. And as for this big thing, I can decompose into f of green plus f of blue. And why can I do that? That's because f is linear. Linear map preserves the addition, so I can do that. Then you'll see the blue part is 0. You see, it came from kernel, and kernel is a subspace. So this blue vector belongs to the kernel, and kernel goes to 0 vector. So this f of that entire part drops down to 0. So we ended up with f of this linear combination is equal to 0. Now let's use the properties of linear map once more. The linear combination is preserved, so you can rewrite this f of linear combination into linear combination of f of v1, f of v2, all the way over to f of vr. And then now if you look at the final statement here, it's a linear combination of f of v1 to f of vr adding up to 0, and this is basis. Bases have two properties, generators and linear independence. And generators, we already proved those. We are now proving linear independence, so we are using the properties of linear independence. This is basis of image, so they are linearly independent. And we have these linear combination equal to 0 vector, so all the coefficients are now 0. So all the green coefficients are 0. That's what we got so far. All right, we are almost there. All the green coefficients are 0 means this entire part is 0. Let's resume. That entire part is 0, so we have green 0 plus this linear combination is equal to 0. Now, u1, u2, u3 all the way over to uq, those are the bases of the kernel, and therefore those are linearly independent. Linearly independent, so each coefficient is 0, and here we go, they're all 0. So earlier we proved all the x's are 0, now we prove all the y's are 0, consequently everything is 0. We have the linear independence as well. In short, we completed proving that this is a basis of V, and we can count. There are green vectors and there are q blue vectors. Add them up, what do we get? We have r plus q, and that should be the dimension of V. So yes, r plus q equals to n. By the way, this number r, the dimension of the image, is called the rank of the linear map.